Hello, we are going to look at another aspect of rotational motion. It is an important one because it has to do with conservation of some physical quantity. You may remember there was a principle called conservation of linear momentum, or conservation of momentum. In the conservation of momentum, that's why we used problems like collision was accessible. We were able to do a lot with the collision problems. Uh, and similarly here you would see there are a lot of problems become very simple uh, because of this conservation principle, right? So just to recall, uh, conservation of momentum, it came from a very similar principle, right? You had a J, um, and this was a force plotted in time, and you looked at the area under the curve, all right? Or you integrated force with time. So this was equal to change in momentum, which is P. So if you look at the J initial to final, then you have Pf minus Pi. This picture is the same as that, right? So and these were, if I look at this net, so this was the net, and this was net. So another thing here was we were able to prove that this is net external. So if left side is zero, say if the balls were colliding, so there's a force from one ball on the other, but there is no outside force during the collision process, right? So we were able to say, okay, left side was zero, that's why the final total momentum was equal to the initial total momentum. So the principle came from noticing that in this equation, if J net external loss of writing is equal to zero, if in that situation, I need to figure out what situations are those, right? Sometimes it will be external forces are acting, but over this time period, its net impact is zero. Okay, so then P final equals to P initial. So this is the principle of conservation of momentum. I have a very similar equation here, so I can apply the exactly same kind of logic, right? You can say if this is zero, so very similar. So principle will be if for some reason I looked at all the impulses from the external forces, and they added, subtracted, and became zero. So there is a I to F here, and so this is like LF minus LI, it's like that. So I can think of a period between Ti and Tf. If this is equal to zero, this left side, which has to do with forces and torques, then obviously right side has to be zero too. Then right side says Li, whatever I had angular momentum initially, is equal to Lf. So I don't need to worry about what happened in between, because I worried about that by making this, this be true. And so this is the principle of conservation of angular momentum. And you can see that torque will, you already know that if the torque is zero, so the torque is zero, then angular momentum will be, this impulse will be zero, right? So if I have a situation like this, torque is just zero, and this is Ti and this is Tf, then J will be zero. That's obviously true, right? The area under this is zero. You may remember that torque will be zero when lever arm of a force is zero, which means any force if there is some rotation axis here, and if the forces are all going through the axis, their level around be zero. So all of this situation, even if there is external force, but it is going through the axis of rotation, then their torques will be zero. So the force don't have to be zero, okay? So one thing to notice here, over here the force had to be zero, all right? Here the force doesn't have to be zero, even if there is a force. So that makes this principle very powerful, okay? Even in the presence of forces, angular momentum will be conserved, because not necessarily just to do with forces, it has to do with torque. Torque has to be zero, and for torque is always R perp and F. So torque can be zero, not just this has to be zero. That can be zero because of that. So I'm saying sometimes you will find this situation being very useful. For instance, when Earth is going around Sun, and so rotation axis is going through the Sun, the force from Sun is actually going through the rotation axis. So if you look at angular momentum of Earth, angular momentum of Earth will be unchanging with time, even if there's a force acting on it. So that angular momentum of this motion around the Sun. I'm not talking about its rotation, 24-hour rotation. So you can see that if you have this situation, then you are going to have you can have a very good principle. We will see if you get to gravitation that an application of this principle actually lets you understand Kepler's second law of planetary motion. It's a deep principle, so make sure you understand this. Okay, let's look at an example problem that we can apply. Say a person M is standing at some distance A from on a rotating platform, which is a disc shape. Okay, so at TI he is there, but he walks towards the center or he walks around somehow, but there's a force between him and the disc, right? And then there must be for him not to slip up, it has to be static friction of some kind, right, between the two. So he's walking, and then he ends up at B at time t. So there is a force, and there may be torque from this onto on the disc, and there is a torque from disc onto him. Okay. However, we'll take it together. So we say system is the disc plus person. So this together system is kind of like a collision problem, right? So you have two systems. So there are the external force on them are not changing. So we can just ignore the external force, right? During this time there is gravity and other things, but they're not changing. So the internal force between them are not going to impact this equation, left side of this equation. So we will see LF equals to LI. It will be applicable. So in this situation, we know how fast it was rotating. We are given the mass, we're given the radius of this and mass of this, and we'll have to figure out what this is. So let's look at how it would be. So at any instant, you can see the person and the disk, they are rotating with the same omega f about this axis. All right. So let's work this out. What LF will look like? LF will look like angular momentum of the disk here, which is half m r squared times omega f. This is the disk. And how about the person? Person will just says point mass going around. So I need the I for a point mass. I for point mass will be just m, and the radius is going in, it's b squared, and it's going at omega f. And on the right side, this is a quite complicated problem. If you were to do on any other way, it would be much harder. Okay, so over here, well, this guy is going in a circle A, but both are going with omega I. So the disk is going, a disk is half mr squared. That's the moment of inertia for the disk, right? And then omega I. And then I have this guy is going in a circular radius A, so its moment of inertia is ma squared omega I. So omega I is common between them, so you can write down omega I as a common between them. So as a omega f is common between them, sorry. Omega f is common between them. And omega I is common between these guys. Here is ma squared, here is mb squared. If they were equal, we would cancel it. So, but they're not equal, and we can solve for omega f, which will be this whole combination times omega I. So I got times omega I going, and I write, it will get net moment of inertia at the initial times ma squared, and the net moment of inertia at the final times plus mb squared. So this will be the answer in symbolically, because all of these are given to us, where he walked. Note the time didn't matter, how long it took him to get from here to there. It only cares about initial to final. So it could have taken 2 days, it could 10 seconds. It will be exactly the same situation. Okay, so I hope this helps you. This is an application of angular momentum conservation. There are more examples worked out in momentum conservation at our website. So if you want to go there and practice more, and there will be more in other textbooks. So hope this whole thing clears up for you. See you next video.